Bismillahirrahmanirrahim. Welcome to PMDC online lecture room. This is Shaheryar Qureshi, Associate Professor of Physics, and today we are going to discuss a very important topic, transformers. This topic is taken from chapter 14, Electromagnetic Induction. Transformer is a device which steps down the AC voltage. And remember, it could only step up and step down AC voltage because DC voltage cannot be transformed through transformers because DC voltage does not change and AC voltage changes. The basic principle of the electromagnetic induction works here, and which says a changing current in the primary coil causes an induced EMF and induced current in the neighboring secondary coil. A typical transformer has an iron core on which two coils are wound. The primary with NP turns. Here you can see that this side of transformer is called primary and this side of the transformer is called secondary. Actually, primary side is the side through which we provide input and secondary is the side from where we get output. So the number of turns in the primary coil would be denoted by NP and number of turns in the secondary coil would be denoted by NS. Similarly, the voltage of the primary would be Vp and voltage of the secondary would be Vs. Now dear students, we have two types of transformer, step up and step down. If the number of turns in the primary coil are less than the number of turns in secondary coil, then this kind of transformer is known as step up transformer because here coil are less and in secondary coil the number of turns are greater, so voltage is being developed from less to greater. And in this diagram you can see the number of turns in the primary coil are greater and number of turns in the secondary coil are less, so voltage has been dropping because it comes from higher potential towards lower potential, and here the voltage is step up because it is moving from lower potential to higher potential. So if voltage is going up, it is step up transformer, and if voltage is going down, it is step down transformer. Now how we will generate the function and how we would understand the function of the transformer. Transformer is based on Faraday law, which says the induced EMF is directly proportional to the rate of change of flux linkage, or the induced voltage is equal to NP and rate of change of flux. So by applying the Faraday law for primary, we will use sin P for primary. So voltage in the primary would be equal to minus NP rate of change of flux. This negative sign is due to Lenz's law. And now for secondary coil, Vs is equal to minus Ns rate of change of flux. Similarly, we have done for the both. Now dividing equation 2 by equation 1, we will get Vs by Vp is equal to minus Ns, rate of change of flux, this is equation number 2, minus Np, rate of change of flux, this is equation number 1. This minus sign would be cancelled with this minus sign, and this rate of change of flux would be cancelled by this rate of change of flux. Our result is Vs by Vp is equal to Ns by Np. Now look at this result. Here voltage in secondary is greater and number of turn in the secondary is greater. And here voltage in the primary is less, so the number of turns in primary is less. It means if voltage in the secondary is greater, then there should be greater number of turns in the secondary. If voltage in the primary is less, there would be less number of turns, and you can see here number of turns in primary coil are less and here number of turns in secondary coils are greater. So the voltage in the primary would be less and voltage in secondary would be greater. Now dear students, we are going to discuss the principle of the transformer. Remember, transformer can step up or step down AC voltage, and the principle of the transformer is to transform power from primary to secondary. So for ideal transformer, power input must be equal to power output. But usually due to losses in practical, the power loss in output is always greater. Therefore, the power output results less with respect to primary because of loss of energy. So power output will always be less than power input. By putting the result for power in primary and power in secondary, we know that P is equal to IV. So IP Vp is equal to Is Vs, as we know that P is equal to IV. So for primary we will write P, and for secondary we will write SS. Similarly, which we have done in equation number 3, we will done it here by equating this equation so that Vs by Vp would be Vp is multiplying here, it would be divided there, and Is is multiplying here, it would be divided there. So our result would be Vs by Vp is equal to Ip divided by Is. Now dear students, look at this equation and result. If we compare this equation number 3 and 4 here, because equation number 3 is also Vs by Vp and equation number 4 is also Vs by Vp, then by equating these two equations we will get Vs by Vp is equal to Ns by Np is equal to Ip divided by Is. Now this is very interesting equation and result. You can see number of turns in the secondary coil is greater, so voltage would be greater, but interestingly the current in the secondary coil is less. And similarly, the voltage in the primary coil is less, the number of turns in the primary coil is less, but here you can see current in the primary coil is greater. How is it possible? Sometimes students thought that it is against Ohm's law, because when voltage is higher, current should be higher because voltage was directly proportional to current. But here, remember, we are not applying the Ohm's law. We are dealing with power. P is equal to IV, and power is the product of current and voltage. To understand this problem, first of all, we have to discuss this whole scenario, that whenever voltage is generated in the power plant, we need step up transformer there. You can see we have only generated 12 kilovolt, and through step up transformer we have step up this voltage to 400 kilovolt. Now for high voltage transmission line we need very heavy and high poles so that voltage could be transformed through them. And then in our city area we need different grid stations. These are the first grade step down transformers which can transform 400 kilovolt to 13 kilovolt. And then we have generated or installed poles in our streets, and there are transformer also on those poles you have often seen in your streets. These transformers are second step down transformers because they step down this 13 kilovolt into 240 volt. Now students, we must have to know that why we need such a heavy installation of poles and here step up transformer and then high transmission voltage lines for the transformations, and then grid stations, and then poles, and then second step down transformers. Let's take this example. Let's say we have to supply 120 kilowatt of power to a certain village, and we have two options for the transformation. One is 240 volt and the other is 24,000 volt. The resistance in the transmission line is only 0.4 ohm. As you know that transformation wire is very thick, and there would be a very less resistance in the transmission wire. So let's see how much current in the wire if it has to take 120 kilowatt of power at 240 volt. P is equal to IV and I is equal to P by V. We have to generate 120 kilovolt. For kilo we have written 10 raised to the power 3, and for voltage we are using 240. So there would be a 500 ampere of the current in the transmission wire, and if this current flows through the wire, now what would be the power loss? P is equal to I square R. For power loss we will use P is equal to I square R formula. Current is 500, we have taken its square, multiply by transmission wire's resistance, which is 0.4. Now this, look at this result. This is 100 kilowatt of the power. It means if we have transformed 120 kilovolt on 240 volt transmission line, then there would be a 500 ampere flows through the wire, and this would generate 100 kilowatt of power loss. Now just imagine we have to transform 120 kilowatt. This is 120 kilowatt of the power which you have to transmit, and 100 kilowatt is being lost during transmission. So we have left only with 20 kilowatt. A huge amount of power has been lost. Now let's come to this second scenario in which we are transforming the same power, which is 120 kilowatt, but now our transformation will be at 24,000 volt. So what would be the amount of current in the wire if we transform 120 kilovolt of the power, 120 kilowatt of the power at 24,000 volt? There would be only 5 ampere current flows through the wire. Now this is a very small amount of current, so the power loss due to the transmission line would be P is equal to I square R. This is the current, and this is the resistance in the wire, there would be only 10 watt of the power loss. Now dear students, in this example you can easily understand why we need this high level of transformation. So remember, the transformation of AC voltage, we must have to use step up transformers so that voltage can be transformed, and for our home appliances we use 240 volt, and if we transform this whole voltage of 12 kilovolt directly, there would be a heavy line losses in this way, and we will lose a large amount of power in the transmission line. Therefore, we must have to install some step up transformers so that voltage could be step up, and then we can transform the voltage through transmission lines. The power loss will be very small in this area, and then we use grids station to take this 400 kilovolt up to 13 kilovolt, and then second step is to step down this 13 kilovolt into 240 volt so that we can use it. Hope you can understand the whole process now. Dear students, now comes to your assignment. Your assignment is how core of the transformer is made, what are the energy losses in the transformer, how we can reduce eddy currents in the transformer core. Thank you very much. Dear students, if you have any questions or queries, you can email us on the given address, or you can use SMS. The WhatsApp number has been given. Hope you will find no problem. Thank you very much.